Not going to paint a picture that FRP is perfect and right and correct and never breaks and is great in every situation. But at the same time, with our experience, we have engineers, inspectors, former fabricators. With all that put together, I mean, we can actually identify specific reasons why there are problems with nozzles and flanges. So part of the issue is that there are just so many, so many different varieties of why a flange fails, and that's sort of the purpose of this presentation. And then I can actually get to ways you can, things you can implement in your own plants or your own specs that can help to avoid this. So I really want to provide specific tangible solutions without just the need for excessive engineering, because sometimes that's in one ear out the other, right? So here I'm going to provide actual tangible solutions. Okay, obviously too many nozzle failures in FRP construction. We need to figure out why that is instead of just sort of living with it. One of the big ones, flange construction and nozzle installation isn't strictly defined. That is odd for people to see. There are certain things that are defined. There are certain things that you would think are defined that aren't. So that leaves room for interpretation or trust. ASME RTP1 has in there, requires the consideration of loads imposed by piping as part of the sustained loading evaluation. But then there's different caveats in there or fine print in there about trying to reduce the loads as much as possible. But not many people are experienced with actually evaluating those loads. It's just sort of a catch-all statement that says you have to. Okay, some of the reason behind this difficulty and this gap of knowledge is rarely are the tank and connected piping provided by the same manufacturer, where the tank designers generally consider the nozzles, the flanges, the end of their scope. Conversely, the pipe designers generally consider the tank flange the end of theirs. So that's where communication can be poor, responsibilities, scope changes, all of that stuff gets unclear. So they just sort of they just want to have that interface point and just be done with it. Figure that's an anchor point and that's it. So then what usually gets done is expansion joints solve the in-between, right? Well, not necessarily, and expansion joint manufacturers and providers don't like when I say that, but we'll get into that a little bit later too, why I have that position. Following slides here, just for a little primer. You've seen some of these pictures before, but I'm just going to show some of the common flange nozzle failures, and you can see through these that there's, you'll see the variety of reasons, the variety of failures that can happen, so that the more varieties that can happen, obviously, the more likelihood that something will happen. If you could just isolate it to one specific issue in a flange, well, we could probably safeguard against that. Well, there's like 4 or 5 different issues that you commonly see with flanges and nozzles. So one obviously is torque. Cardinal rule for FRP that you hear a lot: don't bolt a raised face flange to a full face flange. Either use filler rings or then use a lap joint flange. Lap joint flanges are really, really good. There are some difficulties behind them, but as far as sealing, especially sealing gaskets, because we heard yesterday about trying to reduce that area as much as possible, that's essentially what you're doing with a lap joint flange. So we are fans of lap joint flanges. Don't ask me how to design them. They're not currently approved design in ASME anywhere, so that's another gap that we're trying to fix right now. So the left picture here is a prime candidate for hub cracks. You see the gap there, and it did. Bill made comment that you've seen this picture a lot. It gets the point across, I would say, of a pretty bad flange and a pretty bad crack, because not only do you see the hub cracking that you commonly see, that's really the first place is going to break, but you actually see some cracking through the radial direction of the flange as well, which is a little bit more unique. That takes a good amount of over torque to be able to do that. This is probably one of the most common FRP failures for flanges, but I'm here to say it is completely preventable, not very simple, not quick, but it is preventable. Another way flanges and nozzles fail is just simply from overload. That could be from connected piping, heavy valves. Jeff was talking about that a little bit this morning. Differential thermal expansion, things like that, where you're putting too much load, you're hanging too much weight on that nozzle. It could be going up or it could be down with thermal expansion. But that's another way nozzles fail. So it's in that, not in the flange itself, but actually in the connection laminate. So that's another little wrinkle there. It could be from poor engineering. We heard Steven say earlier, the drain piping on some of their headers is very small diameter. So sometimes he was saying he's seen failures because they're just wrenching down on that valve to try to open it or close it, and they end up breaking it. What we see here is a U-bolt that's sort of bolted tight to that. So if you have thermal expansion there, it's not allowed to grow. That connection there is not very strong at all. It could be gusseted. That certainly would help. But yeah, that tight U-bolt there is not allowing anything. So that's just like a poor engineering decision, which you could see. I mean, obviously that's been repaired at some point and is leaked at some point too. As an aside, Jeff alluded to it, do not bolt U-bolts directly to FRP pipe. Commonly you at least want a little bit of a gap, a little bit of freedom of movement, but you also do want to shield the pipe too, so you don't want steel in direct contact with FRP, but that's just an aside there. Another common failure is just due to lack of reinforcement. I mean, it could be coupled with engineering deficiencies for sure, but all of these can cause failures. So, I mean, honestly, do it right the first time, because when these are 50 feet in the air and inaccessible, your choice to repair becomes a lot more difficult, because it's just you can't access it. So you end up accepting a lot more. Just don't walk underneath that leaking nozzle, I guess, if it's 50 foot up in the air. So just do it right the first time. A little bit more rare, but we have seen some failures due to bond length. Now this vessel did have other issues to go along with it, but where you just have a pure sheer tear off of that nozzle, just the insulation laminate was not long enough to hold it in there. It's very rare, I say that, because FRP is very strong with a shear bond, I guess, in comparison. I mean, it does have its limits, unless it's poor surface preparation. But in this case, what we really see is that it's such a short bond length, and that's why if you're doing a manway, there's no need to have a short projection length. It doesn't need to be 6 inches. Make it 8 inches. Make it 10 inches, because if it's a thick flange and a thick vessel and you're trying to get a 6-inch projection, it's hard to get an overlay behind there, and definitely harder to do it well. And then you have voids or gaps in the laminate, which can promote debonding. And finally here, sometimes you just have poor insulation. Maybe not good enough surface preparation. I think Tom covered yesterday maybe about the tool that they have for shaving the insides of these. They can be good joints. They are quicker to assemble than butt joints, and I know Shaheen was urging to go in that direction if done properly. Our experience is that adhesive joints like this don't handle bending as well as butt joints. So direct tension, very strong joints. In bending, you have to pay a little bit closer attention to that. Okay, so it would help everybody, I think, if we show what nozzle installations actually look like. So obviously we have the flange here. You may have this picture in mind that these should be installed like steel nozzles, where it's just a perfect weld right there that's closing up all of the gap. And that's where you'd be thinking wrong. There's always going to be a gap there. And depending on the fabricator, the hole may not be very tight fitting. So you have a sometimes larger gap than other. There is tolerance definitions in RTP1 that you could follow, but it's not zero, and that's sort of the point of this, is there's always going to be a gap. So I like to say, think of this overlay almost like a piece of tape attaching. So if it's only on the outside there, you're always going to have a little bit of a gap where it lays up. They might fill in that gap with putty and maybe make a radius so you can have a nice smooth transition. That's non-structural. It's not attaching anything. So everything there is just attached by almost like a piece of tape that's trying to hold on there. What are the loads that we're worried about here? So number one, we have an outward load, a radial load. It could be from internal pressure, piping loads. Bolt torque does that too. We're just going to go through the mechanics here and how this is actually reacted by the nozzle, because then it might clue you in to why you're having some of the failures you are. So you put a torque on that, or a radial load outward. Well, you get a bending moment on the flange trying to twist that one out, where you're going to get the max stress in this location. The load is then transferred through the overlay, that tape that we were talking about there. So it's got to transfer through that shear bond area to get down to the vessel, where it's finally reacted at the vessel, where it creates a bending moment here, and you get that peel point right there. So you're trying to peel up that piece of tape. If you don't know, FRP is very weak in peel. There is guidance for the sort of pound per inch peel allowable. It is very low for FRP. And just sort of a frame of reference, for a 24-inch manway, just hydrostatic pressure alone, 8.5 psi is enough to fail the RTP1 peel check. So it's like a 20-foot tall tank. If you just had a 24-inch manway on the outside, it technically would not pass the peel check. Now there's ways around peel. I'm going to talk about that a little bit later, but that just sort of gives you an idea of, it doesn't take a lot of pressure to exceed the allowable peel for FRP. So a quick call back to this one, just to sort of talk about the realities of where these stresses are realized. So we saw this one before, where the failure was from a poor bond. Like I said, somewhat rare in comparison, but more common on shorter projections just because it's harder to get in there. This could be from inexperienced bonders, poor environmental conditions, poor surface prep. They're all contributors to this. But what you more commonly see from excessive torque or radial load is the issue seen in the hub region itself. So this is just an animation of the realities of where the high stress regions are. So when you put the flange under high outward load or excessive torque, the flange bends inward, outward, and the max stress you can see there is just being highlighted red. You've seen plenty of flange cracks so far. You see it exactly in that region, so it's as predicted. So this may even be the sample that Tom passed around. This is another favorite of Maverick here, but I don't even know if you can see it. There's a fine hairline crack there, and if you guys saw the sample, you'll see that it actually did go all the way through the laminate there. When you're just looking at it from the outside, obviously, Adam, it's hard to know just how bad that is. In a couple slides, I'm going to show actual flange fabrication, how they lay up the layers, and that could actually exacerbate how bad that crack actually is, how deep that goes into the laminate. But yeah, you might look on the outside and say it's a minor surface crack, but it almost went through the whole flange, but it's again, completely preventable. Okay, so not only is the hub a high stress region, it can also be an artifact of poor flange fabrication. So what we see here is a detail out of RTP1. It's of what we call an integrally molded flange, where basically they lay up the flange and the nozzle as one. It's not two different components bonded together. But this is going to help illustrate why this is a problem. So this is essentially what a fabricator is going to do when they're making a flange, is they will lay up a layer that make the flange face and then run up the nozzle neck. So they'll do a couple of those to create the flange face and the nozzle neck. And I'll say the most customary way is to then do what's called rings. So the ones going up the nozzle neck are risers. The ones just filling up the thickness are rings. So typically you get twice the thickness of the flange as you would of this region, just because you're supposed to alternate rings and risers. So that's common. So you just do a ring, you'll do a riser. You'll do a ring, you'll do a riser. You'll just keep doing that, and that way you build up the flange thickness, you build up the hub, and then you also build up this sort of tapered transition down there as well. Now from the stress contours, we know that the high tensile stress is in this corner there. So we need directional glass, which is the benefit of the riser going up the nozzle neck, to make sure we're handling that stress, or else it's just sort of breaking a resin bond there. There's that last layer. That not great sketching, but you get the idea of rings, risers, where it's best to alternate. You would think this is in a standard somewhere. I have yet to find it in a standard somewhere. As a matter of fact, I think in some European standards, Dale could correct me if I'm wrong, I think there's some European standards that actually say otherwise. You don't have to alternate rings and risers. But this is sort of a pet peeve of mine, is where in North America we assume that the standards say something about this when in reality they don't. So the problem is, once the flange is made, you can't tell if they mess that up. There's no way of telling if that's a good flange or a bad flange until it breaks, until you cut it up. So here's some examples of bad flanges. A flange may look great on the outside. If you're not speccing them right, who knows what you're going to get. You could get just a lot of filler putty in there. You can just get glass that they're just sort of cramming in there and laying it up just to get the thickness, just to trick you, just because once it's done, you can't tell exactly how they did it. Whereas you have a well-built flange, and this one is a flange on pipe instead of the integral flange, where you have a pipe wall that's just sort of your mold now, and then you're laying up on that. So you don't really have to build the nozzle neck at the same time, but you end up with probably a little bit thicker nozzle neck, but again, alternating rings and risers. If you buy the flanges on the left, which you may not know, but you can spec that to avoid that. You can watch them making these to make sure that they're alternating the layers well. But if you buy the flanges on the left, the flange failures are much harder to prevent. So cross-sectioning of a bad flange, but again, you could not tell until you cross-sectioned this. You just knew on the outside that you had a crack, but to what Adam's point was before, maybe if you cracked there, how deep does it go? Do I know, is it going to leak? Is it going to break that flange? Is it going to break that nozzle? Well, you can see here, as I sort of sketch in rings, 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 okay, a little bit of a riser. Okay, a little bit of a riser, but what did I do there? I had to break up that riser too, because when we burn that out, so put it in the oven, burn out all the resin, you get a little bit of clearer view, but here we go, even a little bit clearer. Are there any risers in that high stress region that we were talking about there? What they did is they had to sort of machine that back because maybe it was a T, or there was a T close by where they had to join the flange to a T, and they needed to put a secondary overlay on this one. So they maybe machined it back, and they didn't want to encroach on the bolt hole, so they had machined it back so they can get an overlay in there. By doing that, they took out the only risers that they had in there. So again, once made, no idea. You have no idea how bad that flange was made. Now, side note, it doesn't mean that well-made flanges won't crack either. This is where we give the standard, have good torque procedures, use the right gaskets. Using very hard gaskets, I would say anything over probably about 700, 800 PSI seating stress gets to be pretty challenging on FRP flange design and getting it to seal. So we try to stay with a little bit softer gaskets, and there was a good presentation on that yesterday, but from that presentation yesterday, you can see that the torque ranges that he was giving you to minimum to seal were pretty low. We have follow good torque procedures because you will crack a well-made flange as well. So that's the radial load causing that crack in the hub there. Well, what other loadings are we worried about? If you have a lateral load that ends up creating a bending moment, the same sort of peel load is realized down there. So now it's sort of additive, right? Because we have the peel load that was generated from pulling out here, plus the peel load generated from the bending moment from the load going that way. So it's a little bit additive in that sense, but you have that same concern with peel there. So we're just looking at the nozzle connection itself now for the next few slides. So the result of this excessive moment on this nozzle. Believe it or not, the installation on the left, I mean, it doesn't seem like it should be correct, right? It seems a little bit flimsy, but there are certain cases in RTP1 where this type of an installation is okay. Now, you should have an internal overlay on that to seal that up. I've been in a lot of your plants, and there's not always overlays on the inside. Sometimes it's post-installed, you don't want to get on the inside. Sometimes it's high up, you added a new nozzle, and you couldn't get on the inside to seal that up. So just from a reinforcement perspective on the outside, technically that is okay in a lot of RTP1 designs. Not all nozzles need repads. So when we animate this, you can see the realization of the peel load there. You see the high stress, the red load there that's trying to pull it out. Don't worry about magnitudes, just look at the stress contour there. So calling back to this failure, which was due to excessive load, connected piping, thermal expansion, some heavy unsupported equipment that you could see there. Well, when this one failed, you can see that's what that peel load looks like. It wants to peel away from the vessel there. So some simple steps to strengthen the nozzles that you guys as the owners or the engineers can simply make here. So we're getting into those. So here's a simple detail from RTP1 showing two different installation styles. Now, look at how perfect that overlay is. It doesn't actually show that radius there to show how imperfect that is. So this is just a perfect bond. It looks really, really good. But as an aside here, the left side shows what we call a style A repad, wherever that's shown. Right there. Style A is much more like a steel repad, like a doubler plate that you'd see in a steel construction, where they're just really reinforcing the hole. So they put the reinforcement pad first, and then put the overlay on to laminate the nozzle to the vessel. Where conversely, a style B puts the attachment laminate on first, and then you put the reinforcement on, which is reinforcing the hole opening itself, but it's also reinforcing that joint there. So we're going to get a little bit of more in depth into these different styles, just as an example of what the magnitudes are. Looking back at some FEA studies here, so we're looking at the style A repad first here, where the green is that repad, just like that doubler plate here. So we're just doing that same load as that previous example where we're getting that hot spot. So just here, for the same load, the stress is 59% less than if you just had the overlay, the red alone, which is good. Deflection is 30% less, great, but you still see there's a peel concern there. We didn't do anything to really solve that. If we look at a style B repad, where we run the green repad up the nozzle neck, the stress and deflection is even better. Stress is 484% less than overlay only. Deflection is 278% less you can still see a red hotspot here. There is an artifact, I would say, that's not easily shown here, even easily calculated, where if you put a big stiff joint on the outside that's so thick and stiff that can't rotate, to really be able to peel, you need to rotate it out, right? If you're just pulling straight out, maybe you have a little bit of peel along that bond line, but eventually it just can't really rotate out. So yes, if you make that outside joint really, really thick, that might fix you in a peel situation, which is sort of needed with a dual laminate construction, but that's a separate topic. So in certain scenarios here, the nozzle on the left is perfectly acceptable per RTP1 designs. It doesn't look like much, and it's not, but in certain situations that is perfectly acceptable. Whereas a nozzle on the right, a lot more robust. It's a style B repad where it runs up the nozzle neck to reinforce that connection. Both may handle the tank's loadings just fine, but which do you feel more comfortable loading up? Obviously the one on the right. So back to address that peel concern, we're trying to get rid of that red hot spot there. There's a couple ways to do it. You can just make the outside joint really, really thick. You can put gussets on to strengthen the attachment. Now standards will tell you anything 4-inch and less needs to be gusseted. In section 10, it's anything 6-inch and less needs to be gusseted, which is good, but the gussets are pretty thin in general. They're really only there to stiffen the nozzle neck. So the case where Stephen was saying, if you open or close a valve manually and just rip it off. So those gussets would have helped to strengthen that nozzle neck alone. But there's other things you can do with gussets. You can make them structural. You can make them as thick as you want. You can extend them up to the OD. Traditionally, they go about an inch short of the back face of the flange. When I have a process nozzle, I like to extend the gusset to the OD just to give it a little bit more strength in bending, protect that flange face a little bit more. The better way to eliminate peel is to have an internal layup. This effectively eliminates peels. It's the strongest connection to me. Internal overlays should be standard. I've said that before. A lot of times it's just corrosion barrier replacement, maybe with a little bit of mat extra in there for structure. It's really not intended to be loaded up like it is in this situation, so you can add a few more structural layers to the inside. That's really common with the 24-inch manways, where I said was a peel concern, is to put an internal structural laminate on there. So you can see in that box, do you see any red? No, so that's not the hot spot anymore, so peel is essentially eliminated. Internal projections help strengthen nozzles too. It's just a little bit more robust connection, but you can see here some reinforced with an internal structural overlay. Those are a lot stronger. Those aren't going to peel. So here it is, as advertised in the title, and I'm not done, by the way, but Maverick solutions for preventing failures. So in your specs, this is what you can do. Add internal overlays with some structural layers. Non-negotiable, just have them do that. I mean, there are certain cases where they may take exception. If it's just a vent or something, maybe you don't need a structural overlay, but I'm talking more here on process nozzles where you're hooking up piping to it, or if it's a large diameter. I would say recommend or require a style B repad over a style A. Regardless of what the calcs say, you can tell them to reinforce whatever you want, and it's not breaking the bank to tell them to just do a 1/4-inch minimum reinforcement. RTP1 says if you're less than if the calculation says you need less than something, I don't know, 0.13, so an 1/8 inch of reinforcement, you don't have to put any on. So if it says you need 0.1 inch of reinforcement, technically you don't have to put anything on, because per the calculation, it says that the shell is thick enough on its own, it doesn't need its own reinforcement pad. But then you lose the benefit of what the style B reinforcement pad is actually doing for you. I recommend gussets to the flange OD. I didn't put it in here, I'm running out of room. You can also make thicker flanges. Standard flanges on tanks are 50 PSI rated. Just because you have a class 150 drilling, that's the drilling pattern, that is not the pressure rating. So a lot of tank nozzles are just going to be 50 PSI standard. Manways are going to be less. You can require 75 PSI rated flanges if you know it's a process nozzle. You can go 100 PSI. There's some that do 150. That just gets a little problematic with spot facing and things like that. But yeah, you can require thicker flanges. Don't forget, manufacturing specs are still necessary too, right? For quality, to make sure you're getting those rings and risers alternating. You're not getting, risers, cut through when you're back facing, or you're not doing your risers first and then filling in with just rings, which we see that too. So mandate your manufacturing specs to do that, alternating rings and risers. And then the installation specs still necessary for torques. Low loads, it takes a lot of time, I'm not going to lie. but do torquing, the crisscross pattern that everybody's heard about. We recommend torquing in about like 25 to 30, 35% intervals. So you're going to go 25% of the torque, the first crisscross pattern. Next one, you're going to go 50, 75, 100. You're going to do another one, then maybe a clockwise drilling or torque pattern to do the final seal. If you want to come back after an hour and do it again, you're going to see that gasket is also relaxed a little bit too. So you're going to retighten those up. So don't just do all the torque 100% in one shot and think you're going to seal it. You're just going to pinch that gasket right there, and then it'll relax over time. That's that for that. Now, I got a lot of engineers in the room, and there's a common question of like, why are my allowable nozzle loads so low? I can't get so deep into it here, but I want to explain why. If you ask a tank manufacturer, hey, give me your allowable loads so I can do my pipe stress analysis on this and figure out, maybe I don't need an expansion joint. So they want to know why the manufacturer is saying, well, just put an expansion joint. We don't have to do that. The allowable loads are 0, right? RTP1 does say this, and I alluded to it before. Fine print, loads imposed by piping and ducting and other external imposed loads need to be designed for. Fine print in the back, the manufacturers must have slipped this one in there in one of the non-mandatory appendices, that vessel nozzles should be joined to piping through a flexible connection or a flexible piping system. At this point, many throw up their hands and just throw in expansion joints. I'm going to revisit this in the last sort of section of this presentation. But first, I want to address the allowables and why it's not so simple, straightforward to provide allowable nozzle loads. Just with a simple example. So 14-foot diameter tank, keep it simple, all type 2, alternating mat and woven roving, simple shell design for, I don't know what I use for hydrostatic. We're looking at a 6-inch nozzle, and I put a 0.271 Repad on there. I'm not looking at hydrostatic in this, and for what it's worth, I am assuming a perfect connection, that glued connection essentially between the nozzle and the shell, meaning I'm expecting the overlay to be doing its job here, but we just want to look at stress in the vessel and what the loads are doing. Okay, if I just look at one direction, that radial load that's going out, and I just want to put 1,400 pounds on there, which the reason I got 1,400 is that's 50 PSI internal pressure on, let's say, a blind that's on that. So it's going to be pulling out at 1,400 pounds. So to not exceed 1,500 PSI stress in the tank, which is about what the allowable might be for a type 2 construction, if I'm in the red, then I'm overstressed, and I don't see any red there. So 1,400 pounds is technically okay in that direction only. We want to look at a longitudinal moment here. So this would be a load force going this direction that's going to sort of rotate around the nozzle that way. We can put up to 525 foot-pounds on that, which if anybody's done some nozzle load analysis, you're going to look at that, you're going to say, I want that. I would love to have that high of a load. I have nothing red here, so nothing is over the 1,500 pound allowable stress. And then circumferential moment on its own, which is a load going this way, a force going that way, you can get up to 450 foot-pounds without having anything red there. Again, these are all in isolation. Does that mean the allowable nozzle load should be 1,400 pounds, 525, 450 foot-pounds? Well, no, because now you're combining all three. So that sort of makes sense. If you now apply all three, we'll look at how red it is. Okay, so now we know we have to take into account some combination, and also sort of keep in mind that the flange needs to be rated for any loads you're putting on there too. And that's why I recommend process nozzle, maybe make it a 75 PSI rated flange to handle a little bit extra load. If we just said, okay, 50% of the max loads together, we'll divide them all by 2 there and load it up. Okay, I have no red spots. So for this particular case, that would be about an allowable nozzle load. Now I don't have any hydrostatic pressure on that, which is going to put a little bit more radial load on that, so keep that in mind. And I'm not telling you these are the allowable loads for the 6-inch nozzle. Don't hear me there saying that. But that's why if you sort of decreased the radial load a little bit, one of these could go up, and it works for the other way too. So you might be able to have a 400 foot-pound circumferential moment if your longitudinal moment was 50 foot-pounds. So there's some combination there. But now you can see when you're asking a manufacturer for completely generic allowable loads, what is he going to tell you? He's probably not going to tell you this. He's going to go somewhere a lot lower, when we know if there was no moment at all, that's actually 1,400 pounds you could put on that. So that's why the manufacturer is just going to be like, and even when you ask us, hey, what's a good allowable for that? I respond to you, How about you tell me what your loads are and I'll tell you if that's okay. That's usually the better way to do that. But that's why the loads need to be conservative, not zero, but conservative. So now coming back to expansion joints, do you just throw in expansion joints? Do they solve the problem? Are they the silver bullet in all of this? Well, in these two cases, I would say no. And if you're eagle-eyed here, you'd see that there's tie rods on both of these. So let's talk a little bit more about the realities of expansion joints and why I sort of cringe when somebody might just be throwing expansion joints in there to solve the problem of the low loads on the nozzle. So for illustration purposes, pressurize, so you have internal pressure in here, and you're going to put an expansion joint in there, which is essentially decoupling it, because the expansion joint is going to be so flexible. If you want to pull that out without any sort of restraints in there, it's going to stretch that expansion joint out and end up failing it. But these are the loads that are going on when you're pressurizing a piping system with an expansion joint. So if you picture here putting a tank on the left side, so that would be like your flange right here connected to an expansion joint. If we sum the forces on the left side, okay, well, we don't have that other force that was in here before that's balancing this. We only have to deal with those small loads on that small convolution area. So conceivably speaking, this nozzle is low loaded. It's not going to be 1,400 pounds. It's going to be somewhere 100, 200 pounds. It's going to be pretty low. The problem is the right side, you sum all those forces, and they're going to be shooting out that way, so that's going to be breaking that expansion joint by just kind of blowing it out. So there's two logical solutions to handle this. You can put an anchor in that pipe, so now the anchor is responsible for carrying the load of those forces, and you're still unloading the tank nozzle, which is great. Now you have to make sure the pipe stress is okay, because hard anchoring that point, this is obviously just conceptual, but putting an anchor in a system when it's handling pressure thrust, pressure thrust is pretty high when you're getting to larger nozzles and higher pressures. So do you have the steel structure capacity to handle, 5,000 pound thrust with that anchor point? Well, what some people end up doing is just throwing in tie rods there, because what the tie rods are doing is essentially locking down that expansion joint so it doesn't blow out. Well, then what's going to happen? This force just has to go back through those tie rods, which now is going back through your nozzle flange. So now you're back to square one. You just put that load right back on the nozzle. Actually, you put a little bit more because you have the extra force of the convolution area. So, there is some debate on the moment transferred through the expansion joint. I don't really want to get into that right now. There is some debate. Obviously it's flexible. I'm a fan of expansion joints on pump nozzles. It's good to isolate pumps from FRP because of vibration concerns, and you should tie those for the most part. But those are a different scenario than when we're using it here, trying to get flexibility out of that. So that's why I urge caution when implementing expansion joints. They can be used, but not without detailed and competent engineering. Final thoughts here. I already mentioned, but I want to keep hammering this home because this is very important. I promised I would have proven solutions, and these certainly will help. Obviously, specs define the flange construction. How do you want them to make the flange? You can decide. Alternate. We just have general notes. Alternate rings and risers, and that's understood. That's as simple as you have to do. Ensure proper design and testing of flanges. The testing protocol that Tim mentioned yesterday, D5421. You can make a flange, or a vessel manufacturer, piping manufacturer, test their flanges. They do a proof test of torque. I think that's audible, maybe 2 times the torque. Somebody can correct me on this. I think they do a hydro test 1.5 times the pressure to see if it'll leak, and then just a general leak test. So there's different testing you can do for flanges to confirm that you would find out if they're screwing up your flange before it actually gets onto your site. Add internal overlays with some structural layers. That will eliminate your peel. Style B repad over style A. That just does a little bit more to reinforce your nozzle connection. If you did an internal overlay, you could probably get away with the style A repad. It's probably okay. You'll tell me RTP1 allows style A repad, so okay, then I guess we technically have to allow that too. But if you add the internal structure, that's going to help a lot with peel. 1/4 inch minimum reinforcement pad thickness. Like I said, it does not break the bank to do this, regardless of what the RTP1 calculations say. The cost for this front end analysis, it's cheaper than expansion joints. Expansion joints are expensive. They're a maintenance item. They may end up leaking themselves. It's cheaper than all the extra hardware for that, or installing new structures and anchors to handle those thrust loads. Cheaper than spring cans, cheaper than repairs, cheaper than outages, cheaper than lawsuits, just by following these simple things with a little bit more reinforcement. Your vessel manufacturers aren't going to no bid. They're not going to gouge you on doing these few things. Most of them do it anyways. Like Shaheen was saying, the reputable manufacturers, they don't want these issues at their nozzles. It just makes them look bad. Gusset your process nozzles regardless of size. So I'm saying process nozzles. So if, like I said, if it's a vent, don't worry about it if it's 6 inches. But if you have a 10 or 12-inch pump connection, gusset it to the OD. Put some structural gussets in there. It's not going to hurt anything. It's going to strengthen that nozzle, give you a little bit more belt and suspenders comfort. And then finally, the torque procedures. Talked about that, but go in intervals, 25, 30% at a time, crisscross pattern, finish with the clockwise pattern. That's going to get you your best seal. So I was told to be provocative with my statements here, so I'll read it if you can't read it in the back. Right, Jeff? Provocative. Nozzles and flanges fail because they are allowed to fail, not because of a deficiency in the material. So yeah, we've talked a lot about failed flanges, but it does, and I said yesterday when we had the return from the breakout, it does not have to be that way. Technically, you guys, I hate to say it, are allowing these to fail, either hands off or you've heard that they just fail, you just have to deal with it. There are things you can do, and hopefully through this you've learned some steps you can take in your own sort of processes to figure out or to mandate how your flanges and nozzles can be a lot more reliable.